Hello, academic stars around the globe. Welcome to Caltex Academy. In case you're new, my name is Julius, and thank you for joining us today. On our board, we're looking at Kyambogo University, Uganda, course unit 4, year 1, mathematical physics. And the question says, prove that the magnitude of A cross B is given by what you see on our board here. So the second part is B, show that the area of parallelogram having diagonals of these vectors is 5 root 3. So this is a question given to me as a request from one of the academic staff who is pursuing Bachelor's of Science in Physics and Mathematics Education in Kyambogo University. So you can also place your request in a comment section and I'll get back and work it for you for free. Please support my work by also subscribing to the channel, share the video with a friend, and with all this said, let us go on and start looking at this question. So question part A is asking us to prove, and that is Lagrange's identity. So here in this identity states that if you have, we can state in two ways, like A, of course these are vectors and a different notation, and this academic staff will take the notation maybe the lecturer is using. So you can have this arrow up here representing this vector cross B vector. Also, this can be given the same as A square and B also square vector. So this is subtracted away, A vector dot B vector, and this is also squared. So the product of these vectors A and B squared minus the dot product. So that is one thing you have to note. I don't know which symbol you are using. The second option would be our A cross B vector, and we put in our magnitudes there. And when we're using that, then we shall have something like A vector also square, and we put on the side of magnitude also this vector and square. Make sure the square is outside the magnitude here, minus into our A. Of course, this is a scalar, and we have that also squared. So since we have this in terms of A cross B in this magnitude, I think something is missing here in this question, and that is a square. There is a square somewhere here. We'll also have the same square, and that is equivalent to this, and that is how Lagrange's identity states. So using this, we can also write this form in terms of a matrix. So with all this, let's go ahead and start doing our work down here. So firstly, we need to copy our vector here. That is A cross B. And of course, in cross product, firstly, we need to get this alone before looking at the magnitude. So here we have that, and it is squared. If we have cross vectors, then it must be in terms of sign. So we can even say let theta be the angle between the vectors. And these vectors are those A and B. If that is the angle, then what we are writing here will represent our theta, which we have just mentioned here. Therefore, A cross B in terms of what we have selected here, term is vector B also is multiplied by sine of our angle theta, but remember it is squared, so we'll have also a unit vector here that is showing the direction always for cross product. And for dot product, we don't have this here, and that is one thing we also need to mark in our working. So since this one is squared, we also have to square this side here, and we move on to continue simplifying this. So we know here that when we square this number, it is like distributing the 2 to each of these individual numbers. We have 4 numbers here, the unit vector, the sign, and then B together with A. So let's go ahead and do that. For the first one, we have A vector, and that is squared. So we have B vector also squared, and sine also squared theta, and n is also squared, so we can do so by having it as dot like that. And we know that when we dot this unit vector, we get 1. So in our next step, just gonna this off. Now, having written this, we can replace this from our trig identity sine square theta plus cos square theta equals 1. So when we make sine square theta, the subject will have sine square theta equals to 1 minus cos square theta. After that, where there is sine square theta, we can replace it by 1 minus cos square theta, and let's go ahead to do that. So we have our A vector square, then B also vector square, and this time we're replacing our sine square by 1 minus cos square theta. And this one has gone to 1 because of what I just mentioned here. So I'll even go ahead and say that is 1, the same thing. Or just ignore the 1 because 1 times anything remains that thing is solved. After reaching to this stage here, the next thing we can do is to distribute this by multiplying through. Opening up this bracket, so we have here A square. When you multiply by 1, of course it brings that. So we have B also square, and our subtraction sign comes here, multiply that inside. We have also A square and also B square times cos square theta. Now after that, we can go ahead and factor out this square away, and if we factor that, maintaining this, and by the way, we can also repeat writing this. So there we have here A multiplies by A, that is this term, and the second term here is also B multiplies also what? B vector, then this is minus. So from here, as we take out this square, we'll create a bracket here, and we have our vector A times vector B cos of theta. So what have you noticed here? This is a dot product. If you have a vector A dot vector B, your result will give you exactly this one here. This vector A and B, and the angle between, that is cosine of theta. Now since we know that, then we can replace exactly what we have here, and we have our A times another A here, and the reason why I've just repeated it instead of writing this form here, Tyler will see that in diagonal we have two terms. One is the top element and then the other element in our 2 by 2 matrices. So we have here B vector, and this multiplies another B vector, and minus. So here is our dot product already, where we have A and we dot it with B. We also square. We can repeat writing this one, the same thing here. So we have 4 terms just like this one. Remember here, this term is 1, like this is 1 term, then the next is this term. So from here, we can also go ahead and split this, but of course we know that this is the same as A dot B and also A dot B. So without wasting time, we need to write it back in terms of a matrix determinant. Therefore, we have our A cross B is written as, so of course, determinant is given by this symbol. These terms come from the leading diagonal, where we bring the first one here, A, and this one is a repeated value. And the next one here, we take it here to make this leading diagonal complete. So we have that B, we subtract away non-leading diagonal. Non-leading diagonal is A dot B, so we can bring it here, our A dot B, and we multiply with the same thing here to make this non-leading diagonal complete. So for that case, we close it over, and that is exactly like what has been given there, hence shown. And that is the solution for part A of this question here. Let us go ahead and look at part B of the question, which says, show that the area of parallelogram having diagonals of this vector 3i plus j plus 2k and I minus 3j plus 4k is 5 root 3 square units. And before we go and solve this second part, if you have not subscribed to the channel, so your highness by supporting this channel through subscribing, share the video with friends, and let's move on to question part B. And from here, we have 3i plus j plus k. We can let A vector to be equals to 3i plus j plus k. I think that is what has been written there. Let us take a look once more. Maybe we can also say B vector. So represent the next one, because these are the two diagonals we have been told from the question here. So 3i plus j plus 2k. Now, since it's okay, and we know for us to get the area of parallelogram, we need to have area of parallelogram is given by 1/2 of the magnitude of the vector is cross product. So that is exactly what we can use for us to get the area of a parallelogram. And since we know our vector A and B, we can firstly get this cross product before looking at its magnitude, because we know cross product is a vector, so it has both direction and magnitude. So let's first get that cross product before looking at its magnitude. A cross B should be equivalent to a matrix and we're using determinant. So the first row always is for these unit vectors I, J, and K. After that, we can go on and follow the order. A comes first, so we take these values or the coefficients of I, J, K. For the first one, we have 3, and in the middle for I, we have 1, for J, we have 2. Then lastly, the next one here is D. We have 1 as the coefficient of I, the coefficient of J is 3, and lastly, we have 4 for K. And please take note that vector crossings are not commutative, so don't interchange. The one that is mentioned first need to come first, then the second one follows. Now, after us writing that, since we're looking at one question, I will show a little bit of those steps. Let's move on here, and one of the steps here before we start working on, we must make sure that this first element should have a positive, the next one negative, and lastly positive here. So putting this into practice, we'll take this element I being positive, so we can put there, and we're going to multiply this by covering over this first row and the first column. So the remaining elements will give us a 2 by 2 matrix of 1, 2, negative, 3, and 4. Then next, we look at this one here, negative, so we have here minus J, and let's not forget this hat. Also, we cover off these elements in the second column and first row, and the remaining one is 3, 2, 1, 4. Lastly, we'll come to K. K is positive, so we say plus K, and we multiply this by covering off the last column and the first row. We have there 3, 1, 1, negative 3. Now from there, let's go ahead and start rearrange this one here by getting the determinants of these 2 by 2 matrices. So here, to get these determinants, we always multiply the leading diagonals. 1 times 4 is 4, minus 3 times 2, 6. But because of the negative here, this negative times negative becomes positive 6. Then we bring in our vector here and attach. It's good to have number before the vector itself. So we can move the next one and say minus, opening up this bracket, 3 times 4 is 12. Then we say minus 1 times 2 is 2. We can close that and also bring in our J here and remove the last one, that is plus, open up this bracket, 3 times negative 3, we get negative 9, and we subtract away 1 times 1, we get 1 also, and we bring in our unit vector K. So let's simplify what is in the bracket here, and we get our answers 10i. Now this one is 12 minus 2, that is 10. 10 times negative, we get negative 10 in this direction of J. Then next, negative 9 minus 1 is negative 10. That means the positive here is also negative 10 in the direction of K. Now after that, we have gotten our vector A cross B. Now the next thing here, for us to get the area, we need the magnitude of this vector, where we say A cross B is gotten by getting the components of x square plus the component of y square plus z square and the square root. We'll have x is 10 square plus negative 10 also square plus negative 10 also what? Square. And all this under a root. Now when you look at that, I get there under 300. So for this one who doesn't have calculator, let me help you out by simplifying this one in a way of multiplying this 100 by 3 will still get us 300, and you can use distributive law to distribute the square root sign to these two numbers. Because when multiplying is allowed for us to distribute this root sign. Now from here, square root of 100 is 10, and this one is irrational number. We can leave it like that, and that becomes the magnitude of this cross vector. Now finally, we can get our area from what we stated earlier on, that is 1/2 times the magnitude of this vector here. So that is A cross B, its magnitude. So if we substitute in 10 root of 3, and you can see that we can reduce 10 by 2 to 5. And when we divide this, our area is the same as 5 root of 3 square units, as indicated for us there. We're asked to show that the area of these vectors will give us this. Let's check out from the question there and see that for sure it rhymes. So indeed, when you look at it carefully, you will see that the area is exactly the one mentioned here. We have shown that when we cross these vectors, we can get area of that parallelogram, and it's exactly what we've gotten here. If you have watched at this time, thank you for watching, and if you have any other requests, please don't hesitate to drop it in the comment section. I'll get back and make that video for you just like this one here. See you in the next one. Peace out.